What actually happens when you cross the point of no return? The answer doesn't just disturb our understanding of black holes. It shatters the very fabric of reality. Because inside that darkness, time itself stops, and you become a ghost frozen at the edge of forever. But is that what truly happens? Some physicists say you'd be incinerated in a wall of fire. Others claim you'd enter a new universe. Welcome to the ultimate abyss. For more than a century, the event horizon has stood as the ultimate cosmic firewall, a mathematical surface where escape velocity equals the speed of light, and where Einstein's laws apparently break down. Our entire understanding of reality hinges on what happens at this border. It's not just a theoretical puzzle. The black hole's deepest secret could determine whether information can be truly destroyed, whether our universe is a hologram, and whether we live inside a black hole ourselves. This story begins in the muddy trenches of World War I, where a German artillery lieutenant named Karl Schwarzschild made an impossible discovery. While calculating artillery trajectories on the Eastern Front, he solved Einstein's field equations for a single point of mass. His solution contained a terrifying secret, a magic circle where time itself grinds to a halt. Schwarzschild mailed the results to Einstein in 1916 and then, tragically, died of disease weeks later. Einstein was stunned, but he never believed such an object could truly exist in nature. Schwarzschild's magic circle is what we now call the event horizon. To a distant observer, an object falling toward a black hole appears to slow down, freeze, and fade to red, smeared across the horizon for all eternity. This isn't an optical illusion. Time itself is stretching due to gravity. The Event Horizon Telescope has actually observed this redshift and time dilation in the glowing matter swirling around M87's central black hole, confirming Einstein's wildest prediction down to the millimeter. But here's where it gets deeply unsettling. For the astronaut plunging across, nothing special happens at the horizon. General relativity insists on no drama. The local physics is perfectly normal. You wouldn't feel a bump, see a flash, or even know you'd passed the point of no return. This violation of our intuition creates a paradox. How can you be both frozen on the surface for eternity and sail through unharmed? The answer redefines what it means to observe the universe. Once inside, the real horror begins. In a stellar mass black hole, the tidal forces are so extreme that your body would be stretched into a thin strand of atoms within milliseconds, a process astrophysicists call spaghettification. In 2019, astronomers actually caught a star being ripped apart and stretched into a noodle as it veered too close to a supermassive black hole 215 million light-years away. The event, at 2018 FYK, gave us direct, observable proof of what Einstein's equations had predicted for decades. But the singularity at the center is even stranger. Roger Penrose proved mathematically that all matter inside a black hole must eventually collapse into a point of infinite density, a place where the fabric of space-time rips apart. Yet from the faller's perspective, the singularity is not a point in space at all. It's an inevitable moment in time now. Once you cross the horizon, the singularity lies in your future as unavoidably as next Thursday. You can no more avoid hitting it than you can avoid tomorrow. But that's not the end of the mystery. In 1974, a young Stephen Hawking dropped a bombshell. Using quantum mechanics, he showed that black holes aren't completely black. They emit a faint thermal glow now called Hawking radiation. This radiation carries away mass, so black holes slowly evaporate and eventually vanish. But if a black hole disappears, what happens to all the information about the star that collapsed? Quantum mechanics forbids information loss. General relativity demands it. Thus was born the black hole information paradox, and the greatest scientific war of the late 20th century. For 25 years, physics split into two warring camps. Leonard Susskind battled Hawking, insisting that quantum mechanics must be saved. The conflict resembled a theological debate. Each side convinced the other was committing heresy against nature. The breakthrough came from an unlikely direction, string theory, and a principle as shocking as anything in science. It suggested that everything inside a black hole, every atom, every memory, every shred of identity, is actually encoded as a shimmering, two-dimensional hologram on its horizon. The interior might not even exist in the way we assume. So what would our infalling astronaut actually encounter? In 2012, a group of physicists, including Joseph Polchinski, re-examined the horizon under a microscope. They concluded quantum effects would transform that supposedly smooth boundary into a seething firewall of ultra-high-energy particles. Anything crossing would be instantly incinerated, not stretched. This firewall paradox sent the physics community into a tailspin because it forces us to choose which pillar of modern physics to tear down. Tell me honestly, do you think firewalls exist? Or is the holographic principle the true answer? Comment your raw instinct below. But maybe black holes aren't just destroyers. Einstein and his colleague Nathan Rosen showed in 1935 that black holes could be mathematically linked to white holes, objects that spew out matter and light, through a throat called an Einstein-Rosen bridge or wormhole. If an astronaut somehow survived the singularity, they might emerge in an entirely different universe or a distant epoch of our own. Some cosmologists even speculate our entire Big Bang was the white hole rebound of a supermassive black hole from a parent cosmos. The implications are mind-shattering. This idea gained physical traction in 2013 when Juan Meldacena and Leonard Susskind proposed the ER equals EPR conjecture. It states that every time two particles are quantumly entangled, they are connected by a microscopic wormhole. Wrap this up, and the entire interior geometry of a black hole might be nothing but a giant tangle of quantum threads. So the question, what's inside a black hole, transforms into what is the relationship between information and space-time itself? The answer could unite the two greatest theories in physics. Let's bring this down to a tangible timeline. You cross the event horizon. Time, for the outside universe, accelerates to infinity behind you. You see the entire future of the cosmos flash in an instant. Then, if firewalls are real, you're annihilated in a blink. If not, you experience a few seconds of terrifying tidal stretch before reaching the Planck scale, where space and time lose meaning. In loop quantum gravity, instead of a point, the core becomes a Planck star, a ball of compressed space-time that rebounds into a white hole after eons, perhaps birthing a new universe. You become immortalized as a Big Bang. But how could we ever probe this hidden realm without falling in? Gravitational waves from merging black holes carry a ring-down signature, the dying vibrations of the final black hole. In those oscillations, general relativity predicts specific frequencies. Any deviation would signal quantum structure at the horizon. Similarly, the Event Horizon Telescope's shadow image of M87* already rules out many exotic theories, but the next generation could detect photon rings that have orbited the black hole multiple times, carrying faint echoes of the interior physics. Another profound clue comes from the second law of black hole dynamics, proven by Hawking in 1971. The area of the event horizon always increases. This mirrors the second law of thermodynamics so perfectly that Jacob Bekenstein proposed the horizon's area is a measure of its entropy, and thus, its information content. The LIGO-Virgo collaboration confirmed this law in 2021 by analyzing merger remnants, showing horizon areas grew precisely as predicted. This suggests that the horizon really is a storage device, a cosmic hard drive whose bits are Planck-length pixels encoding everything that ever fell in. And then there's the supermassive black hole at the heart of our own galaxy, Sagittarius A star. Observations show it spins at a staggering 84% the speed of light, dragging spacetime around it like a whirlpool. This creates an ergosphere, a region outside the horizon where nothing, not even light, can stand still. If you navigated just right, you could extract energy from the spinning black hole to power a civilization. But venture a hair too close, and you'd be swept into the same inescapable current as the star S2, whose orbit has now shown us the clearest evidence of an invisible, superdense monster. Roger Penrose, beyond proving singularities, also hypothesized cosmic censorship. Nature forbids naked singularities, always cloaking them behind an event horizon. But what if? If a naked singularity existed, light could escape from the infinite density, allowing us to observe quantum gravity right here with telescopes. Some supercomputer simulations suggest that certain violent black hole collisions might momentarily expose the singularity, giving us a fleeting window into the abyss. The search for that naked eye has already begun. Whisper/soft tone.